Page 69, we're going to kind of get into the concept of a limit here. Sequence A sub n has a limit L written as you would expect it. For every epsilon greater than 0, there exists a positive integer n rather than delta. So we're going with epsilon n rather than epsilon delta if you're familiar with the epsilon delta definition of a limit. All right. But long story short, if a sequence has a limit, then we say it converges, right? Because I don't want to get too bogged down with whether or not you saw all the different rules for limits. I'm just going to go over the ones that are absolutely critical here, and that is the constant, sum and difference, product, and quotient rules for limits. These properties are absolutely essential moving forward. All right. You should also be familiar with the sandwich theorem. You may be familiar with it as the squeeze theorem, but that's something that you should know as well. All right, but we will go over that in the next page or so. There's a lot of notation on this page, and you're welcome to read through it. Aside from little formatting issues like this, it's pretty informative. I mean, it's very informative, but I think nothing serves the purpose quite like diving into some examples. All right, so let's hop on over to the next page. All right, so basically we're looking to determine whether the limit exists as n approaches infinity for each of these cases in order to determine whether these sequences converge. All right, so what we're going to look for here is the limit as n approaches infinity of b sub n. All right, and so we could list out all the different terms of the sequence if we want, but we could also rely on our knowledge of limits and all those rules and relationships that kind of helped us evaluate those limits. So this would be the limit as n approaches infinity of n plus 4 over 3n minus 2. All right. So you might remember that when you're evaluating the limit of a rational function, that would be continuous cases, but still the idea holds true that if the exponents are the same, the highest exponent on the top compared to the highest exponent on the bottom, then all you're really doing is taking the ratio of the leading coefficients. All right. So as n approaches infinity, this sequence would approach a 1/3. Now we can verify that. All right. So again, you want to make sure you're in sequence mode, but by typing it in, sometimes more trouble than it's worth. But by typing it in, the n plus 4 over 3n minus 2, you can get an idea of what this sequence is approaching for large values of n. So as you increase, you can see that it does seem to be closing in on something in the mid to low 0.3s. All right, so it's just a question of whether that's going to be 0.3 repeated. Right? You go far enough, you'll see that will be the case. But it doesn't take too long before you convince yourself that it will get to that. All right, so maybe instead of going by ones, maybe you go by hundreds. And in going by hundreds, when you go by hundreds, you see that it's getting to 0.33 a lot quicker. All right. So pretty convinced that this sequence is going to converge, again, because the limit exists. All right. So goes right back to this. If the sequence has a limit, then we say the sequence converges. All right. If it doesn't, then it diverges. So the next up would be the limit as n approaches infinity of a sub n, which would be the limit as n approaches infinity of n squared over e to the 4n. All right. So what does this look like? Well, we can do this a couple of ways, but one way involves the quotient rule. So we could find the limit as n approaches infinity of n squared over the limit as n approaches infinity of e to the 4n. However, you can kind of look at this as saying, well, I don't know how helpful that's going to be, all right? Because if I substitute an infinity squared, or in for n squared becomes infinity squared, that's going to give me infinity. And an exponential function has an n behavior that's infinite. So we're looking at something that's infinity over infinity. All right, so it does beg the question, what's going on here? All right, so infinity over infinity, that's usually indeterminate and usually triggers L'Hopital's rule. All right, so let's take a look at what's going on. So n squared over e to the 4n, well, aside from the fact that I have my table settings from the last problem, the domain shouldn't be a concern. Looking at the values that we have here, it does appear to be decreasing to something close to 0 until it becomes, this error it's leading me to believe that this is an overflow error, not the kind of error that is mathematical in nature. It's just the calculator can't handle the computations anymore. All right, so what we could do, we could do a bunch of things, but what we can do is we can start actually listing out the sequence. These decimal forms aren't too neighborly, but what I can do is write it in a more unsimplified form. So 1 over e to the 4th, then the next value would be 2 squared, which would be 4 over e to the 8th. 3 squared is 9 over e to the 12th. All right, and so we can do a quick comparison between the numerator and the denominator. Right? I think it's pretty easy to see. Even without doing the computations, but I'll do it anyway. E to the 12th is going to be monstrous. All right? So the denominator, even though we're squaring the numerator, the denominator is going to largely outpace the numerator. All right? So this leads me to believe that this is going to be approaching 0. All right? So the question becomes, well, how do we take care of this? Well, we could apply L'Hopital's rule, except since sequences are not differentiable, L'Hopital's rule does not apply. All right. Instead, we use a different approach. All right. And so what we have to do is actually express the sequence as a function. All right. So it's kind of, it might seem like splitting hairs, but what we're actually going to do, and I'll actually kind of take you through it. All right, so the theorem, let a sub n be a sequence with a domain, blah, blah, blah. Let f of n be a sub n. All right, suppose the function f is defined for all values, and there so for all real numbers, x greater than or equal to n. So this stuff, so assume it's defined. Then what we could say is the limit as n approaches infinity of f of x, if that goes to L, then we could say the same thing about the limit as n approaches infinity of a sub n. All right, so it's kind of a weird thing to say, but what we're going to do is write a function and call it f of x is equal to x squared over e to the 4x. Then what we're going to do is find the limit as x approaches infinity. All right, so x taking on the role of n. You could leave it in terms of n's as long as you know that n is now taking on the role of a continuous variable. All right, so I don't like that, even though my own notes say to do that. I don't care for that approach. If we're going to write it as a continuous function, write it as a continuous function. So we already know what's going to happen
if we plug in infinity for x here. But now that we've defined it as a function, now this is going to be, it's going to be continuous. So it's going to have a lot of extra points that we don't care about along the way. But its overall trend should be the same as that of the sequence. So I'm going to apply L'Hopital's rule. And if you don't remember or never learned, L'Hopital's rule tells us that if we have an indeterminate case, so infinity over infinity, 0 over 0, 0 to the 0th power, infinity to the infinitieth power, there's a bunch of different ways you could represent indeterminate. But if it's an indeterminate case, then you could apply L'Hopital's rule, which tells you to differentiate the numerator separately from the denominator and reapply the limit. All right, so I'm going to reapply the limit as x approaches infinity. I'm going to run into the same problem though. It's going to give me infinity over infinity, so I'm going to apply L'Hopital's rule again. All right, and that's because if I evaluate the limit, it's indeterminate. It's infinity over infinity. So here, derivative of 2x is going to give me a 2, and I'm going to have 16e to the 4x on the bottom. That's going to give me 2 over infinity, which goes to 0. All right, and that's consistent with the trend we observed in the problem, where if the denominator is outpacing the numerator, oh, I didn't want to hit copy, I wanted to hit resize. If the denominator is outpacing the numerator, then there's every reason to think it's going to 0. All right. So, and we could even, if we go into the other mode, the function mode, we can confirm that. So alpha y equals, put in an x squared. So long story short, too late, if you think of this function as the curve that would go through all of the points denoted by the sequence, that's a pretty good way to think about it. All right. And so with that in mind, wherever this goes, the sequence would also go, just you're going to get a lot of extra points along the way. All right. So let's see, 1 over e to the 4th is the largest value that I need. Yeah, so something like this, and then you can see it's leveling off, but it does appear to be approaching 0. All right, so that's number 2. So 3 involves, right, you got this cosine function, it's oscillating function, and you got the radical function on the bottom. Right, we can approach this in a very similar fashion. The issue is that we you know, when you go to apply a limit here, I'll show you. As n approaches infinity, cosine 5n squared, where are you going with that? You know? And if you take the derivative of it, if you think it's something like L'Hopital's, then cosine becomes negative sine, it's still going to oscillate. Where does cosine go at infinity? We have no idea. All right, not using any kind of direct substitution technique anyway. So what we're going to do is redefine this in terms of x, write it as a function of x, cosine 5x squared over the square root of x. With the idea being, again, that this gives us a sequence of points. You know, maybe it's oscillating, maybe something like this. But the function of x will give us a continuous curve. It'll go through all those points. Yeah, it's gonna give us more than what we bargained for. But in addition to more than what we bargained for, it's going to give us the points that we do want. Right? And wherever this function goes, this f of x goes, the sequence will follow. All right. So what we'll do instead of finding the limit as n approaches infinity, we'll find the limit as x approaches infinity of cosine 5x squared over the square root of x.
All right. Still, we need to know how to find the limit of this. Now, you might remember a nice relation from way back when, and that is that the cosine function, so some cosine function with an argument, unknown argument, doesn't matter, always exists between -1 and 1. It actually doesn't matter what the argument is. The function will always exist between -1 and 1. That has to do with the cosine's amplitude. All right. So what I can actually say here is -1 is less than or equal to cosine 5x squared is less than or equal to 1. And that would still be a true statement. And in fact, if you graph it, it's not always going to be pretty. I'll do a trig zoom, but it does seem to be living between a y value of -1 and a y value of +1. All right, now if I wanted this expression here to be cosine 5x squared, instead of that I want it to be cosine 5x squared over rad x, I could divide each part of this inequality by rad x. And then once I do that, I can apply my limit to each part. All right, so what I like to do is a little copy-paste action. So the limit as x approaches infinity of each piece Now, we don't know the middle piece. That's why we're here. But the two outer pieces, we can figure those out. The variables on the bottom, constant on the top, those are both going to 0. So what we just concluded is that the limit as x approaches infinity of the cosine 5x squared over rad x has to be between 0 and 0, which is a nice way of saying that it's got to be equal to 0. All right, so I'm just going to move some things around, create some more space, because I never give myself enough room. All right, so this has to be equal to 0. If the function is going to 0, then all of the points along the sequence would have to be going to 0 as well. So the limit as n approaches infinity of cosine 5n squared over rad n would be going to 0 and therefore converges. Right? And I don't believe I ever made a note on the previous one that that's also converging. We have another sequence is just unnamed, but it could be very well a sub n, b sub n, whatever. So we're looking for the limit as n approaches infinity of this expression e to the n over the cube root of n. Now if I plug in infinity here, I'm going to get something that's indeterminate. All right, so that's telling me that I should be thinking about letting this be some function of x, or letting some function of x trace through the points generated by the sequence. All right, and so that's what we should be limiting as x approaches infinity. All right, so we could apply L'Hopital's rule, or at least attempt to. In doing so, I hate when that happens. In doing so,
I would get e to the x, no help there, over 1/3 x to the negative 2/3, still with a limit as x approaches infinity. Alright, so a little keep change flip action. Limit as x approaches infinity. 1/3 becomes the 3 e to the x, and then we would have x to the 2/3 power. Alright, because that negative exponent is going to shoot that x to the negative 2/3 up to the top as in addition to the 1/3. Alright, so now what we have here is something that, well, wouldn't fit L'Hopital anymore. We're looking at 3e to the infinitieth times infinity to the 2/3. In any way you slice it, this is going to be infinity, and this is going to diverge. Number 5, same general idea, but let's take a look at this first. You see a negative exponent there, so I'm going to rewrite this as 1 over e to the 3n to the 5th, and then we'll have that tangent stuff. N squared minus 9, or inverse tangent I should say. So we're going to find the limit of this as n approaches infinity. Now, one of our properties for limits, and I'll just do a little copy paste action here. Copy, paste. Limit of a product is equal to the product of the limits. Alright, so we're going to find the product of these two. And hopefully that'll get us where we need to go. Now, as n approaches infinity, it looks like in this piece here, inverse tangent, yeah, it is what it is, but on the top we're going to have some sort of infinity going on there. But on the bottom, we're also going to have some kind of infinity going on there. We'd have to investigate what that's going to boil down to. Alright, so we'll cross that bridge in a sec, but let's take a look at this one. If I substitute in an infinity for the n here, I would be looking at 1 over e to the 3 times infinity to the 5th power. So it's essentially saying, if I can make that look like a power, it's essentially saying 1 over infinity, which goes to 0. So there would be some limit that exists over here, I'll call it L, but that's going to ultimately be multiplied by 0. If it was infinity, or 0 itself, or negative infinity, the only thing that wouldn't play out would be undefined. But we know that the tangent function exists, right? Inverse tangent, as long as the n value isn't 3 or negative 3, and this is saying we're going to infinity, so we're not worried about that, we're going to get something that exists here. So the limit will be equal to 0, and therefore this one converges. So for number 6, we're looking at something that's very similar to number 3. So I'm going to treat it essentially the same way and look at this as a function of x. So x squared sine of 3 over x squared, knowing that where the curve goes, the points will follow. All right. So we know that sine of a exists between -1 and 1. So it follows that the sine of 3 over x squared would exist between -1 and 1. If I multiply through with an x squared, that middle expression becomes the x squared sine of 3 over x squared. Alright, and so then what I would do is I would apply the limit as x approaches infinity.
Right, I kind of cut out the step where we bothered trying to see what the limit of b sub n would be as n approached infinity, because we knew how that story would end. All right, so for the low end, we get a negative infinity less than or equal to the limit as n approaches infinity of the middle expression which in turn would be less than or equal to positive infinity, which is not conclusive. Inconclusive? Inconclusive. So we need a different approach, but fortunately we have a function to work off of. All right, so I typed it in here. Now if we go to zoom 6, you see that it does appear to be leveling off somewhere. It's just a question of where does it level off. So what do? We can start with a table setting of 0 and a delta table of 1, so second window. And as you scroll along, you see it appears to be leveling off at 3. So it's a pretty safe assumption that the limit pause for dramatic effect as x as I wrote n approaches infinity for some reason. Yeesh. Alright, so as x approaches infinity would be equal to 3, so therefore now I need the limit as n approaches infinity of b sub n will also be 3, and therefore it converges. Now that's based off a graphical approach. All right, so it's a question of how you want to get that evidence into your submission. I only need a quick sketch of the graph. All right, so something like this, a little funny business over here, and then shooting on out over there, and then something indicating that that's at 3. All right, now if we did this on Desmos, it'll be a little easier to see. Y equals x squared sine of 3 over x squared. All right, nice looking graph. If you're doing this digitally, any kind of digital submissions, you could always do a copy-paste job of any graphs from Desmos. It's a good-looking graph right there. Pretty clear that that's leveling off at 3. If you trace along the graph, click on it and trace or drag along it, you can see that it levels off at 3.